Welcome. This is the sixth video in the series on Principles of Radiographic Exposure 1. Last video we discussed properties of the radiographic image. In this video we will explore the secondary properties in forming a radiographic image. If you remember from video 3 in this series, we learned that the primary factors are KVP, mass, which is MA in time, and distance. A secondary factor is all the components that go into and affect the quality of the image, but that the operator has limited control over. They also have potentially less influence over the final look of the image. This is not to say that collectively the secondary factors can't significantly affect the final image, just that individually they influence less. With this established, it is important that the radiographer be aware of all the potential secondary factors. We learned about what makes up the digital image in the last video, which was lesson 5 of this series, image properties. And we discussed spatial resolution, sharpness, and distortion. Now we can expand this slightly and look at factors that play a role in creating the final image. So we expanded the visibility, which are like photographic properties, okay, and into density, which is just the brightness, and contrast, and geometric properties, which is like the sharpness of the image. And we talked last time about distortion, which now we separated into size and shape, which we talked about in the last video, and recorded detail. We'll explore these more right here. Recorded detail, which is a spatial resolution. Okay, these can be used interchangeably, essentially. So we'll talk about geometric unsharpness in this video, and in the future we'll talk about motion unsharpness and receptor unsharpness, and we'll expand on these things here. Okay, and we'll get into some of the photographic properties in this video. The first secondary property that we'll look at is the focal spot. In the X-ray tube, there is a rounded loop of tungsten metal that is called the cathode. Across from the cathode is a spinning plate called the anode. On this spinning plate, there is an area that is made of tungsten and is called the focal spot. So on the anode side is the focal spot. Typically, a diagnostic radiology X-ray tube has two focal spots of different sizes. They are referred to as the small and the large focal spots. The small focal spot will be around 0.4 to 0.6 millimeters, and the large will be 1 to 1.2 millimeters. These are typical values. They could be slightly different. Each of the focal spots corresponds with a cathode that is equally proportioned. So remember, the cathode's on one side, it's typically negatively charged, and the anode's on the other side, and it's referred to as positively charged. Depending on the size selected, the sharpness and distortion of the image can be affected. So depending on what focal spot we pick, it can change the sharpness, and it can distort the image in different ways. The resolution of the image is highly affected by the matrix and pixel size of the system. Okay, but the focal spot can play a role in it. So the smaller the focal spot size selected for the exposure, the sharper the image will be. So the smaller the focal spot that's selected, this would be the small focal spot here, or this would be the small cathode here. The sharper the image. So we can see here that this is would be the cathode side. There's a thing called the focusing cup here, and this would be the large cathode. Okay, and across from it, corresponding to it, would be a small focal spot and a large focal spot on the anode. We'll get into this more during radiographic physics in that playlist, in that series. But for now, we'll say that, as we know, sharpness of the radiographic image should be maximized, then why not use the smallest focal spot available? As we just said, that the smaller the focal spot, the sharper the image is going to be. The reason is that 99% of the energy put into the tube during X-ray production becomes heat, as we learned before during the video on X-ray production in this series, which I believe was video 3. We'll get into this more in the radiographic physics playlist too, about this heat exchange and all that. There is a limit to the exposure, to the mass that the tube can safely utilize based on the KVP selected. And this is more in the physics too, okay? But for now, this is all we need to know, is that there's a limit to the mass that can be selected and the KVP. The larger the focal spot, the more surface area there is on the anode that it's utilizing. And as we could see in the other one, the cathode is larger too. And the more heat the cathode and anode can handle without damage. The larger the focal spot selected, the higher the exposure available, is what this amounts to. And the smaller the focal spot, the lower the exposure available. So right here, this is the main reason why we might select large focal spot over small focal spot, because we need a higher technique based on the KVP, or we need a higher KVP and with a mass. So we need a higher technique overall, so we need to use the larger focal spot perhaps than the smaller focal spot in certain situations, even though the resolution of the image will be lower. With this, the larger, thicker body parts like the abdomen, chest, pelvis likely will require the larger focal spot. This is a trade-off with spatial resolution, as we just discussed, and the needed exposure. So the trade-off is with spatial resolution and needed exposure. Since the abdomen is a low spatial resolution image, okay, the subject is low resolution, right? This is not an issue on the final quality of the image for a part like an abdomen. With smaller, less thick body parts like hands, ankles, etc., the smaller focal spot can be used because we don't need as much technique for these body parts because they're not as thick. Since these parts require a higher resolution to visualize bone edges and hairline fractures, the smaller focal spot is advantageous. So this really works to our advantage anyways, right? It's almost like they designed the equipment for us to use it in a certain way that maximizes the output, which is a quality image, right? So the larger the part, we need to use the larger focal spot typically, and it's typically okay. It typically works out okay because they're lower object, okay, frequency. The object frequency is lower typically in these parts. And when we need something that's much more sharp, and we get that by the small focal spot, the parts are typically smaller. So let's talk about the focal spot, the actual versus the effective. So you may see these terms in your books and whatnot, and we need to know the difference between what the actual focal spot is and versus the effective. The actual focal spot is the physical area on the anode where the electrons from the cathode are focused. So the actual focal spot is the physical ring of tungsten, okay, that's on the anode, and it's the thickness of it, okay? So it's where the electrons are focused from the cathode, okay, by the focusing cup that we just saw on the earlier slide. The actual focal spot size will not change as it is a solid visible place on the anode. So if we were able to visualize the actual tube and we could look at the anode, you could actually see the focal spot on the anode. So the actual focal spot can be visualized. It's the physical thing on the anode. Okay, the effective focal spot is a focal area which is projected to the detector. All right, so the effective focal spot is the projection of the focal spot towards the image. Okay, the effective focal spot is affected by the actual focal spot size, so by the size of the physical size on the anode, and the beveled angle and the location it's projected to the detector. So the angle of the bevel of the anode and where it's projected inside the image, okay, along the image. The image quality can be affected by the size of the effective focal spot. So we have a diagram here that I came up with of the things we were just talking about. So this is the electron beam from the cathode, the focus electron beam from the cathode, and this is the actual focal spot. So this is the anode, this is the bevel, the angle on it, okay, and the actual focal spot size is in red right here. It's a physical thing, okay? It's a tungsten that's here on the anode, okay? The effective focal spot is what's projected towards the image, okay? And we can see here that this is the size of it right here, of the actual focal spot, and this is the projected one, okay? The central ray will be the only, is how we measure the actual focal spot. So the very center of the field of view is what we say is the effective focal spot, okay? But this can change over the field of view. So we said that it changes with the angle, all right? So this is how it changes. So the less the angle, up to 45 degrees, the smaller the effective focal spot will be. The actual focal spot doesn't change. Up to 45 degrees, it should be roughly the same size. In practice, it may be slightly different, but in theory, it's the same size, okay? Because it's coming out here, and each one is reflected exactly 45 degrees. It will be getting trigonometry a little bit and everything, okay? But it will be the same size as the effective and the actual, okay? At 45 degrees. So, and when the angle gets less and less and less, the effective focal spot will be smaller. Okay, so why not just make the angle as little as possible? Well, again, there's a trade-off between these things, all right? So we'll get into the how it changes across the image, and then we'll talk about that right after this. Now we know that the effective focal, now we know what the actual and effective focal spots are. Now we'll learn about the projected focal spot. So this is the term for how it is across the image, okay? The effective focal spot is the center focal spot, okay, off of the central ray right here. So this is the only actual effective focal spot. The actual focal spot is the place on the anode itself, okay, and this would run all the way around the anode here, okay, in a ring, because this is going to be spinning, so it's going to be hitting all these areas, but they're just showing it this way in this image. The projected is how it's projected across the image, okay, so all these are projected focal spots, and it's projected differently across the image. So as we talked about, the effective focal spot is seen from the eye or along the length of its projected size of it will change. Okay, so as it's seen across, the projected size will change. The farther from the central ray the focal spot is projected, okay, so across the field of view, as it's being projected to the cathode, the larger it will become. All right, the larger the focal spot will be projected. All right, the actual focal spot is going to stay the same. The effective focal spot is going to stay the same because it's only right here in the central ray. It's only this one point. It's theoretically small too, like a point is in math, but for us it's this size, okay? And as you go to the cathode, it's going to become larger. As you go to the anode, it's going to become smaller, the projected focal spot. So these are just different terms that may be used, and we need to know the difference between them as they're being used. Okay? Let's go ahead and talk about another aspect that affects the quality of the radiographic image, and that is the anode-Hill effect. The anode-Hill effect is the lessening in the intensity of the beam across the image due to the angle of the anode and characteristics of X-ray production. So we talked about the angle of the anode, how the less the angle is, the greater, the smaller the effective focal spot will become. Okay, and then also the greater the spatial resolution of the image will be, right? So why not just make it as flat as we can? The anode-Hill effect comes into effect here, is why. So across the image, the further away the central ray is on the anode side, so the further away from the central ray towards the anode side, the relative intensity is decreased of the beam, and as the angle increases to the cathode side, the relative intensity increases. This is due to the way that the X-rays are made. It's also due to the angle of the anode. Okay, so as the electrons hit the anode, hit the focal spot on the anode, their X-rays aren't created directly on the surface, okay? They penetrate slightly into the anode, and then the X-rays have to escape through there. So if they escape towards the cathode side, they have less material to go through, okay? They have less of the metal of the anode to go through to escape to make it as part of the primary beam. If they, towards the anode side, so as we go farther and farther this way towards the anode side, they have more material to get through, okay? So if this angle was greater, right here, if this was just straight up and down, everything just to this side of the central ray would have to go completely through the anode to get out, and it would have to go farther and farther due to trigonometry. It's taking the hypotenuse, okay? So it would have to go farther and farther. The greater the field of view, the more opened up it is to go through the anode, okay? So, but if there's a little angle on it, it doesn't, this effect is minimized, okay? I hope we can visualize that here with this, all right? So X-rays aren't created directly on the surface. They are created slightly into the anode, all right? And then they have to escape it. They're absorbed through the metal here, so the intensity, the energy that they contain becomes lower as you go this way, and also the quantity becomes lower, okay, as you go towards the anode side relative to the cathode side, okay? And we call the central ray is usually just labeled as 100%, okay? It's just labeled as 100%, and that's the intensity, we would say, okay, of the beam. And everything this way would be less. It can get all the way down to 40% or so, depending on how the angle is here and how wide the field of view is, and it can go all the way up to 130% of the central ray, okay, intensity. So with this, we'll talk about the anode-Hill in practice. We'll talk more about the anode-Hill effect in physics as well. But here, the anode-Hill in practice, larger body parts should be placed towards the cathode side of the tube. So let's think about that. What did we just discuss? Why should larger body parts be placed towards the cathode side? Well, it's more intense on the cathode side, right? The beam is more intense on the cathode side. The part is larger. We need more X-rays on that side to make it through the patient to the film, okay? And the smaller part, not so much. So, on a shoulder of a humerus, okay, so the shoulder of the humerus should be to the cathode. So if we're doing the humerus, the elbow isn't quite as thick as the shoulder, not typically, and the elbow should be on the anode side where there's less intensity. Due to the angle of the anode, the effective focal spot changes and the relative intensity of the beam changes across the field of view, okay, as we've already discussed. Now let's talk about focal spot size and spatial resolution. With all their factors remaining the same, the smaller the focal spot size, the sharper the recorded detail, as we learned about before. Therefore, there's a trade-off between the heat dissipation and the needed sharpness of the image. As the focal spot size increases, the spatial resolution decreases. This is an inverse relationship, but the amount of heat X-rays that can be produced increases. Okay, and this is for tube safety. So the focal spot size and the heat dissipation are directly related. They might not be linearly directly related, but we'll learn more on that in the physics lessons. Okay. Also, if the projected focal spot is larger than a single X-ray capture element, which we call del, in the image receptor, this can produce incorrect readings and low spatial detail. If you don't know what a del is, what a capture element might be, these things are discussed in the Principles of Radiographic Exposure 2 playlist on this channel. The projection of the focal spot can cause object blurring. This blurring we call penumbra. So the projection of the focal spot over the image can cause blurring that we call penumbra. This brings us to umbra and penumbra. From the actual focal spot size, the X-rays are emitted at various angles. With these different angles, the same edge of an object will be recorded several times in different locations. The recording of the object in its true location is the umbra, and the spreading of the edge is known as the penumbra. Penumbra is the blurriness due to geometric effects of of the image. So as we can see here, it's geometric properties, the sharpness, and the geometric unsharpness. So penumbra falls under this category right here. We'll talk about the relationship between penumbra and the OID-SID. The amount of penumbra would change with the SID and the OID, as well as the focal spot size that is utilized. The greater the SID, the less penumbra there will be with all the factors remaining the same. The less the OID, the less penumbra there will be. So the closer the object is to the image, to the detector in our case, the less penumbra there will be, and the greater distance that's used, the less penumbra that there will be. Also, the smaller the focal spot, the less penumbra there will be. You can see this if you take a light and shine it at the wall. As you move your hand, if you put your hand in the way, you move it closer and farther away from the light on the wall, it will become more blurry as you get closer to the light, because the OID, your object is the hand, and the image that you're seeing is the wall. So the OID is increasing as you're moving towards the light. As you move closer towards the wall, your hand should be sharper. There's less blurring on the edges of your fingers as you come closer to the wall, as the OID decreases. Also, if you increase the distance that the light is away, or you make it closer to the wall, as the OID, a smaller change in OID will cause a greater change in the blurriness of your hand on the wall, the closer that the light is. So the less the SID is. If you move the light way back as far as you can across the room, now you can move your hand a lot more. Okay, so it's semi-intuitive when you think about it this way. As the penumbra is increased, the resolution is decreased of the image. Okay, so we can see it here, what we just talked about. The greater the OID, the greater the penumbra will be. So this is showing that the penumbra here, this is the edge, okay, and the many different angles that it can come out. The extreme angles is what's being shown here from the target spot. The edge will catch here, in here for the 2, and the red is the amount of penumbra. Okay, everything in between here to here is the umbra. Okay, so it's being represented as it truly is. Okay, in a straight line, straight down. Okay, and the penumbra is everything here. The closer the OID, or the less the OID, the closer the object is to the image, the less penumbra there will be, as we can see from these 2 right here, with the SID remaining the same on those 2. As well as the greater the SID, the less the penumbra will be. Okay, so the SID is less here on the right, and there's a greater penumbra where there's barely any here. Okay, and the OID remains the same between these 2. So that's a good visualization of what we just talked about. There is inherent OID when using a Bucky apparatus, of course. So when you're using the table, you're using the chest stand, there's always going to be some kind of OID. Some factors that create penumbra can be controlled by the radiologic technologist, and others can't. The OID, for instance, that we just talked about. The distance the patient is from the IR can be controlled to an extent, and the distance the source is away from the IR can be controlled. We have pretty set distances that we typically use, and it's set that way for a reason. Okay, we want to minimize that. We use 72 when possible. Okay, and when it's not quite so important and the OID will be less, typically we can use 40, 44. Okay, and this is also due to exposure. All right. The focal spot size can change, but not always. So we have set focal spots. We can use a small or a large, and we should be using a small when possible. But sometimes you have to use the large, of course, right? The angle of the anode cannot be changed. The equation to calculate the amount of penumbra is the penumbra, which is the P, and this equation here is the focal spot size that's utilized. This is the actual focal spot size times the OID over the SOD. And SOD, of course, is the SID minus the OID. So this will be the amount of penumbra. If all factors are the same and the OID is doubled, then the penumbra present will be more than doubled based on this. Okay. And as the SID becomes shorter, this becomes more pronounced, as we talked about with the hand before. Let's go ahead. There's a couple practice problems right here. You can pause the video here. I encourage you to solve these problems based on the last slide. You can go back if you didn't quite get that equation. It's focal spot size times OID over SOD is the equation that's used, and that's the amount of penumbra that's present. So here's a couple questions. It's asking, what is the penumbra? Okay, so a different kind of question that may be given is it gives you the penumbra, and you have to find one of the other factors that isn't given. You have to find the SID that was used. What's the SID unified if these things are this and this? But here we just have where it's just asking us to find the penumbra every time. I also want to point out here that look at the units. So this is in inches, this is in millimeters. You need to pick a unit. I would say pick millimeters. It may matter for the final answer, it may not, but to be thorough, you always want to make sure that everything is in the same units as you're doing it. Okay, and there's 25.4 millimeters in an inch. Just so you know, there's 2.54 centimeters in an inch, which is 25.4 millimeters. So if you go to millimeters, okay, you can divide it or multiply it if you're going to inches or millimeters, whichever way you decide. And the answers will be at the end of the video. All right, so we talked about penumbra, and we talked about some factors. This is a nice chart that says everything we just talked about, okay? So as the SID is increasing, right, the effect on penumbra decreases. The same, it's an inverse relationship with the decreasing, okay? And the OID is directly related. The patient thickness, and it doesn't say how much it increases. It doesn't say by what factor necessarily by, okay? But it just is letting you know the direction that penumbra is going, these things. And of course we want to reduce, okay? So some of the things we can't help the part thickness, right? We can't always change the focal spot size, but we can use a smaller one when possible. The OID we can control up to an extent. The SID is set. We can use longer SIDs if we want sharper things, like for a chest x-ray and things like that, right? And we're using and it's a thicker part, okay? For an abdomen, we might use a shorter distance, even though it is a thicker part, because of the amount of radiation we need to use, right? And we have to also use, most likely, the large focal spot. But that is a low subject frequency area, so it works out okay in these kind of situations, right? But this is a nice chart here that is everything we talked about on penumbra. And remember, the umbra is the sharp of the image, okay? And the penumbra is the unsharpness of the image due to geometric effects. Next, we'll talk about patient factors. So special considerations when taking a radiograph that we need to think about, okay? And these are included with secondary factors. It's a continuation of these secondary factors, is that a radiographer must be able to recognize the multitude of patient and equipment variables and how these affect the image and adjustments that need to be made in order to produce a quality radiographic image. We'll go ahead and we'll talk about some of these factors. We'll start with patient factors. Patient factors include size, shape, and condition of the patient. The thicker the part, the greater the technique required to produce a radiograph of the same quality. Okay, so to produce the same quality radiograph, and the thicker the part, we have to increase the technique. Typically, it's the mass. We'll talk more about that in the next video, which will be video 7 of this series, lesson 7 of this series, which will just only be dealing with technique in that, and we'll really delve into these kind of concepts more. But in DR systems, the electronics of the IR and image processing algorithms can correct for a wide latitude of exposure. So as a radiographer, we get away from using really nice techniques all the time with the computer algorithms, but we need to be using the optimal technique, because we aren't just going through the motions. We are just doing as minimum as we can. We want to use the correct technique and achieve the best quality image. And using the best technique will allow the algorithms to do their best job. Just as we said, it's our duty to use proper exposure. Patients will have different physical characteristics, including physique, general bearing, and body build. Together we call these body habitus. And all this can go into this part of the size and shape. Okay, and so all this goes into distortion, the size and the shape, okay, of the patient. If the patient's very thick, there's going to be a lot of scatter. We can't help that. We can use a grid, we can use the room, we can use buckies, we can make sure the OID is minimal, or we could do an air gap technique, or we could do other things, okay? And we need to be thinking about all these things as we're doing the images. Let's talk about body habituses. We may already know about body habituses, but this is a secondary factor that we need to consider when performing the radiograph. Body habituses can change the position of the internal viscera, the general size of an individual, the makeup of the tissues, and the body wall thickness. There are 4 major types of body habitus. The most common one is sthenic, as we say. 50% of the population is typically sthenic, also known as average mesomorphic. It is a moderately heavy build with the organs oriented as such. And we can read it here. I'm not going to go through all this here, but you can read it here, okay? So it's an average build. Asthenic, which is about 10% of the population, so not very many. Very low percent is the asthenic, also known as very slender or ectomorphic. It is a frail build with the organs oriented as such, okay? With some noted things is the stomach is low and near the midline, okay? These kind of things could be important for doing GI series and things like that, to know generally what a position. So you see the person, you can kind of classify them, and then you can know where to go, okay? Hypostenic is 35% of the population typically, and is intermediate between the stenic and the astenic body habituses types, also known as slender. So this is a slender. So this is very, very thin, okay? And this is just a normal kind of slender build, all right? The person may not exactly present that way, but that is the way their habitus might be, if that makes sense. Similar to astenic, but the stomach, intestines, gallbladder are higher in the body, okay? Hyperstenic is only 5% of the population, so very few are these. It's also known as endomorphic. It is a large build with the organs oriented, where things like the stomach are very high transverse and in the middle, okay? And the lungs are typically short, and the apices are near the clavicles, and they got a high stomach, okay? So this is the hyperstenic. And we can see these things right here. If you're unaware of these things, or you haven't seen them in a while, you can pause right here, I would say, again, and just kind of take a good look. And there's nice diagrams of the stomach, the intestines, the gallbladder, okay, and how the lungs are and everything, okay, and the percentages and the summary of what we talked about in the last slide. Now we'll move on to pathological conditions. So as opposed to the patient conditions, that's just kind of like their thickness. This is kind of the things that they could have that changes what we do. Okay, so pathological conditions is additive diseases or diseases that increase the absorption characteristics of the part. And there's destructive diseases. So there's additive and destructive. And destructive are those that decrease the absorption characteristics typically, and increase or decrease in KVP is desirable to compensate for pathological conditions. So if they have an additive condition where there's an increase in the absorption characteristics of the part, we want to increase the KVP, okay? And destructive is decrease, okay? If they have a destructive condition. And here's a list. Your text will probably show more than this, but these are just some ones that typically come up more often, things like pneumonia, CHF, all right, and then, or emphysema, COPD. These kind of things are destructive, so if we're doing the chest x-ray, we need to be aware, and we will adjust our technique accordingly, okay? And we would use less with the destructive technique, and we'll use a bit more with additive. Perhaps there's the other factors. They may be thinner, they may be larger patient, okay, and it depends what part we're doing too. So all these things need to be taken into consideration when doing a radiographic image. Other patient factors include pediatric patient. We want to use a low KVP and mass. Fast exposure times may eliminate the use of AECs, so we may not want to use AECs. We probably want to use a fixed technique more often. KVP for children under 6, due to their bone density, is recommended to be reduced by 15% of what you might use for an adult, or maybe what you would use for more of what I would say like a fully grown child, where they're a child still, but they're like 14, 15, you know, but they can be larger than adults, so to say, but we still need to be considerate of that, and we should be using less KVP, and we should be reducing the mass, okay? We still need to use enough to obtain a quality radiographic image, but we need to try to reduce the radiation in these patients even more than typical. We just need to be more aware of it. Geriatric patients, exposure techniques may need to be decreased for patients who appear thin and frail. So this is kind of with the asthenic people, but geriatric patients even more so. Tissues may be lower in subject contrast and require a decrease in KVP. They may have osteoporosis going on. They have loss of muscle. Muscle is more dense than just other soft tissue, and these kind of things. All right, so we need to evaluate the patient. Geriatric, we may need to reduce what we're doing. Bariatric patients, now then kind of goes the other way, right? They categorize as obese, increased in KVP and mass typically. In addition, a grid is important to reduce the scatter radiation reaching the tube. So we may want to use a tube. We may want to use a grid where maybe if the person wasn't quite as large, you know, we wouldn't for that particular body part, a knee or a femur or something like this, right? We may want to make sure if we're doing a portable and things that we're using the grid. And we will talk about grids in not the next lesson, but the lesson after, which should be the 8th lesson, video number 8 of this series, if you need to look at that. Now let's talk about soft tissue and contrast media. Soft tissue, sometimes to visualize wood, glass, or a swallowed bone, a soft tissue technique is needed. This is usually a decrease in mass. We would also maybe decrease the kVp. As we can see here with the hand, this would be like a soft tissue technique where we can really visualize all the soft tissue within the hand, okay? So if we're looking for a foreign body, we need to be aware of that, and we need to adjust accordingly. Contrast media, the type of contrast media used changes the absorption. So there's two different types of contrast media. One of them is positive. Positive is barium or iodine typically is used. It absorbs more X-rays within the body. Positive contrast media requires a change in technique. So typically we would raise the kVp because we want to be able to penetrate the contrast that we introduced, and there may be an increase in mass as well. Negative is the other one. So there's positive, there's also negative, such as air decreases absorption. Negative contrast media agents do not require a change in technique at all. This can change the contrast aspect of the visibility. So going back to this, there's the photographic properties, visibility. So this will of course change the contrast aspect when we introduce contrast. That's why we introduce contrast, is so we can get more contrast of the areas that we're looking in, whether it's the vessels or the GI tract. Typically, it could be a joint. It's kind of an old thing that hasn't done much, but you can introduce it into joints too, either positive or negative contrast media. Some additional considerations is projections and positions. So an oblique of an L spine requires more exposure than an AP. And compared with the AP, the amount of tissue should determine the changes in the exposure factor. So how thick, the thickness that we're introducing, right? And it's the same with the lateral, of course. So whichever position the patient is, okay, it's going to change what we're doing. Okay, we may change the kVp on this. If we're using fixed or AEC, the automatic exposure control, it's going to shoot higher on its own. We need to make sure that we're positioning correctly. But if we're using fixed, we need to be aware of this, okay, of what position the patient's in or the projection that we're doing. Cast fiberglass generally requires no change in technique if the patient has a fiberglass cast on. Plaster casts require an increase in exposure factors. We need to increase when there's plaster. There is no standard method for this increase. Typically treating the thickness of the cast as if it were part of the thickness of the part is acceptable. Okay, so we just look at the cast when it's plaster and we say, well, if this was the tissue of the femur or the knee or the wrist, then what kind of, if the patient was this thick, then what kind of technique would I use? That's the technique I'm going to use with plaster. Fiberglass, we don't need to change. Splints are less of a challenge than casts. An air or fiberglass splint requires no change in technique. A wood, aluminum, or solid plastic splint may require an increase in exposure factors, but only if they are in the path of the primary beam. So often the splint is just around a certain way, and the other way is exposed to air. So only if we're shooting, if it's on the patient interior and posteriorly, okay, and their lateral aspects of their finger are exposed. On the lateral, we obviously don't need to increase, right? But on the AP and the oblique, we may. Filtration. We'll go ahead, we talked about all the patient factors, now we're talking about factors of the equipment again. The filtration. Any tube that is capable of exposures above 70 kVp must have 2.5 millimeters aluminum equivalent filtration. So with this, we've added an extra layer of complexity to the manufacturing process of the equipment. And so why would we do that, right? It's not for nothing. Most of the X-rays that are emitted during the exposure are of low energy. In the third video of this series, we learned about the X-ray emission spectrum. If you're unfamiliar with this or need a review, I recommend that you watch it now. So we learned that most of the X-rays emitted are of low energy. Low energy X-rays increase the patient dose, and they only get absorbed in the skin and provide no useful image information. All these low energy X-rays that are produced. And most of the X-rays that are emitted during exposure are low energy, as we just said. This is why filtration is employed, is to filter out these low energy waves that add no useful information to the image. More filtration, the higher average energy the beam will be, but the less X-rays there will be in the primary beam. So what we would say the quality of the beam will go up, but the quantity is going to go down, how many there are, because we're filtering out, we're getting rid of certain amounts, so obviously there's going to be less, right? We need to increase the mass. An increase in filtration will increase the average energy of the beam, but it will also decrease the total amount of X-rays there are. Okay? And remember, a change in the average energy of the beam can change the contrast of the image. The computer is going to correct for it, okay, as your text will tell you, but there can be a change in the image. We could say that the beam is harder. The harder beam, it's a more energetic overall beam, okay? So this is a exposure taken with less filtration. There should be at least 2.5 because it is over 70 kVp that this is capable of, so there should be at least 2.5 millimeters equivalent of filtration. And this is with increased infiltration. So the average energy, if we added all these up and how many there are, and we averaged it out, how many X-rays there are, and the average energy of them, the average energy would be higher. And we can see the peak is shifted, so it's pretty obvious from that. And but the amount is less. So let's talk about where the filtration comes from. Filtration is a diagnostic images, must be a minimum 2.5, as we talked about. This is achieved through inherent and added filtration. Inherent filtration is the glass envelope of the tube, the oil in the tube housing, the beryllium housing, the reflective mirror, and the plastic windows of the collimator. So all these things are the inherent filtration of the tube, and that's what's present. This would typically add up to about 1.5 millimeters equivalent. Each manufacturer may be slightly different depending on the thicknesses of these things used and the exact materials that they use. Added filtration is a thin slab of metal, typically aluminum, which are installed in between the X-ray tube and the collimator, or a slot in the collimator, and it's typically the 1 millimeter equivalent. Okay, it needs to be a minimum of 2.5 millimeters equivalent for diagnostic radiation. That's X-ray tubes that are above 70 kV. Another secondary factor is the generator output. This won't be an in-depth explanation of generators, as the parts of the tube that we just talked about aren't in depth. This subject of the generators is multifaceted, and we will explore more about the generators in the radiographic physics playlist. The generator is collectively the complex of circuits that receives electricity from the wall, from the mains, as we say, and changes its characteristics to a form that the X-ray tube can utilize for X-ray production. The energy coming in from the wall, from the plug, isn't useful for X-ray production. So there are two different types of generators, half rectified and full rectification. Half rectification will need a higher technique to be set, at least 2 times the mass compared to the fully rectified units. Okay, and as we said, we'll explore what all these things mean if you're not quite sure in the radiographic physics playlist. Full rectification can be 1 pulse, There can be 3 pulse, 6 pulse, 12 pulse, or high frequency, with each one in the order above needing less technique to be set as they are more efficient at X-ray production. So as we go along here, if the 1 pulse, 3 pulse, 6 pulse, 12 pulse, high frequency, less technique needs to be set with each one of these generators. With the more pulses that there are for the fully rectification ones. I think most are just fully rectified now. This is the generator here. This is a fluoro unit as well. So there's multiple things. It's usually in the corner. It we'll explore more in the physics playlist, but it does its purpose, okay? And we don't really think too much about it. But from room to room, there may be a difference, and it may come from the way the generator is set up and the technique that you use. Here, so that concludes the secondary factors that we're going to talk about in this video. Here's a picture of what we talked about and everything that goes into it. So to produce a nice clean image of a $20 fake bill, right? We need the image receptor factors, which we'll talk about in the Principles of Radiographic 2 exposure playlist. We need the geometric factors, which we talked about in the last video, and also some now about distortion, okay? And then subject factors. So we talked about the contrast, if there's contrast media, what the parts are, the thickness, the density of the parts, atomic number of the parts, and motion available, which we'll discuss in the technique playlist, okay? So this is a good picture of it. This is another one of things we talked about in addition to the one that we've used throughout the lesson, okay? We talked about the visibility, contrast, the brightness, okay, noise, and then the sharpness, all right? And shape distortion with the penumbra and the way that it's being projected onto the image, and the focal spot. Okay, so all these things are the secondary factors that go into play. The primary factors, again, to remind, are KVP, mass, and distance. These are the primary things that we can control of the radiographic image. The secondary factors are things that we have less control over, but collectively can change what we do greatly, okay, depending on on what's present, right? And so, and what technique we're setting when we're doing when we're exposing, okay, when we're taking an image. Let's go ahead and we'll have the answers to the problems that we talked about before. Let's go ahead and answer those problems that we had before. And if you didn't answer them, I encourage you to do it now. Get the practice in, go ahead, answer them, and see what you come up with, okay? And so the first question was, an exposure is taken with an SID of 72 inches and a patient OID of 3 inches. The focal spot size utilized was 1 millimeter. What is the amount of penumbra present in the exposure? And then it goes on to ask, what is the penumbra with a 6-inch OID? So all the other factors are the same, and we can just change it from 3 inches to 6 inches, all right? And we go back to the equation that we used before, which is focal spot size times OID divided by SOD is going to give us the penumbra present on the image. And of course, SOD is SID minus OID. We plug these things in, and remember that each millimeter is 25.4, each inch is 25.4 millimeters. So we plug that in right here. We keep the one the same, of course, because it is already in millimeters. And with the first one, with the 3-inch OID, we get 0.043. Now the difference here in the second part of the question is that the OID is 6 inches. We were thinking maybe it would just double, so it would just be 0.086, right? If we just double the OID, the penumbra is going to double. Well, you know, it doesn't quite work that way. It goes up by more than that, okay? It's not 0.086, it's 0.091 millimeters is going to be present when we increase the OID. So it increases more than the doubling of the OID. Okay, so we can see that here very clearly. And in the book, your text, that may be expressed as micrometers, so we just go 1, 2, 3, and it'll be 91 micrometers. Okay, and exposure is taken at an SID of 40 inches and a patient OID of 6 inches, the focal spot size utilized was 1 millimeter. What is the amount of penumbra present in this exposure? So everything from this last question here to this one, the only thing that changed was the SID. So we can see how big of a difference that change in SID makes on the total penumbra. For whatever reason, you know, maybe we're supposed to shoot at 72, but we're at 40, and we're going to increase the penumbra a pretty significant amount here. Okay, so there's quite a bit more penumbra on this using the 40-inch SID, as we can see, compared to the 72-inch. Okay, in this case with these factors. Now for the second half of this, we are using the 0.5 millimeter focal spot. Okay, and we just plug everything like this. Again, the same, everything else with the OID and everything's the same. And in this case, it does half. So the focal spot size, when it's halved, it is a direct relationship, okay, which we have less control over the focal spot size that we're going to utilize for the things we talked about before, and it's already built into the machine, these set amounts. The distance we can change. Okay, we can go a bit farther back or a bit closer if we feel like we need to on these things. There are set distances that we should be using, of course, but we can change that. Where the focal spot size, you know, it's just kind of set. Okay, so if we use the smaller focal spot size compared to the large one and all the other factors are the same, now we've hashed it. We actually have less penumbra here with the smaller focal spot. Very interesting. Than with the larger focal spot and the longer SID with the OID being the same. Okay, so this concludes our lesson on secondary factors of radiographic exposures. In the next lesson, we'll talk about technique, and we'll explore those concepts further.